go to the website, you'll get the full syllabus, and I highly encourage you to read that. So I'm Mary Jane Perry. I'm down at the Darling Center, and I'm just getting over pneumonia. I'm not contagious, so I'm going to be here for the lecture and the first lab, and I hope within 2 weeks I'll be back and be here for all the labs. So those of you in labs, the 4 o'clock and the 6 o'clock and tomorrow, I apologize, I'm not going to be here, but I don't think I can stand up that long. So I'm really happy to be here. I've been teaching this class for just about 10 years, and it's probably my most favorite class. I was flying from Tobago to Trinidad one time, and the flight was scheduled to leave at 9:30, and at 9 o'clock, the pilot looks around and he says, well, everybody who's here is here, let's go. So everybody who's here is here. Shall we go? See if we can get out a couple minutes early. Okay, so now I'm supposed to remember to turn this on. It is on, but I'm supposed to remember to plug it in. Is there a way, Jim, to tell if I'm good? Am I too loud? Am I too loud? Okay, yeah, unplug it. Okay, so bear with me. There may be a couple of things I forget. I'll try not to. So I'm Mary Jane Perry. I'm down at the Darling Center. That means that you can't come to my office easily. But I am on email almost all the time, and we can figure something out if you need to talk to me. So don't hesitate to email me. Just put whatever you do, please. I don't get as many emails about Viagra as I used to, but I do get a lot of spam. So please, please, please put SMS204 in the header so that I know that it's important and that I look at it. Otherwise, sometimes I kind of don't. So just do that. So what's this part of the class? So you're going to have a major break. I know you had a big change. You know, you did a lot of physics last time, and I'm sure had a really good time. So this is really like a whole new class. So there'll be some new roadmaps, some new guidelines. And in terms of what's today's class about, and I want you to think about what this is, and I'll tell you at the end. So what's the class about? And I'm going to go over that for a couple of minutes and talk about the goals of the class in particular. The second thing about the class is you're scientists. And so you should be curious and asking questions and challenging. Challenge authority. Challenge me. Challenge authority. So in order to be able to do that, you got to speak of the language. And that, in our case, units is a really important part of the language. And so I'm going to be stressing units. I'm going to be stressing conversions and all sorts of things. Hey, you guys want, there's 2 handouts. Could you make sure he gets it? Thanks. So there'll be a big stress on conversions. And then, you know, you hear a lot in the newspaper and on the radio and on the web, you know, who are you going to trust? And one of the big questions you should be asking is, how do you know if a measurement is correct? And one of the things that I want to get across in this class is, how do you know your measurements are valid? You know, we're scientists, and we want to make sure that what we do, what we report, what we measure is correct, and that we're not just making it up and winging it. And so this class is giving you a guideline and a roadmap for how you know to have valid measurements. The short version of the syllabus directs you to the website, and the reason that there are things in the full syllabus and on the website is I'd like you to read them. And so please do take advantage of that. And so this is where you go. If you have problems, just shoot me an email. So our view of the ocean today really relies on good measurements. You know, as I mentioned, you see stuff in textbooks, on the journals. So here's a textbook that Dr. Townsend wrote. Here's a journal from the European Copernicus Society. Here's something from the LA Times. So we rely on having good measurements. And where do the values come from, and how are they validated? So that's a big part of the whole question here. So let me go into what's this class about. Metrology. So metrology is the science of measurement. How many people have never heard of metrology as a word? Yeah, I mean, it's kind of a cool word. Geeks love metrology. I am sorry, my father was a double E, I'm a geek. And it's the science of measurement, and it comes from the ancient Greek to measure and alology. And it really becomes the basic for trust. And so you want to know if you can trust something. So we're going to spend a lot of time on metrology. And then the second thing is we're going to spend time on phytoplankton nutrients, including salts in seawater. How do we measure them? The nutrients for phytoplankton are the building blocks of life in the ocean. And everything in the ocean depends on phytoplankton. Nutrients are important in the carbon cycle, so that has to do with our climate. They're important in terms of the marine food web, and that is the rest of the life in the ocean. And it's important in terms of water quality, whether you can drink the water. Everybody's been hearing about Flint, Michigan. Just because you're a marine scientist doesn't mean that you can't go attack a freshwater problem, because water is the new oil in terms of water is what we're going to be fighting about. And it's water, whether it's in the ocean or in freshwater. And we're going to use chemistry to measure one nutrient concentration. And a lot of what we'll do will be an analog for how you do other things. And the reason we pick phosphate is it's a simple reaction. You add a reagent and you get a reaction within 10 minutes. And so that helps in a 2-hour lab. The other part of this is continuity. Every week will build on the last week. So we want you to be engaged, participate, and really make that connection. If you don't make the connection, I can't make it for you. And so one time I was teaching the next class, SMS204, and I asked somebody about a standard curve, that we had made nutrient measurements in the Damariscotta River. And somebody said, I never heard of a standard curve. And I went, you're breaking my heart. This is what you're going to do. And this is, again, part of the basis for trust and knowing what you're doing. So there's a continuity within this class and within your education. You may have heard of the concept of KSAs, knowledge, skills, and abilities. The knowledge from this class is going to be measurement science and water chemistry. The skills and abilities are going to be best practices, data analysis, and evaluation of data from other sources. And these are really transferable skills, knowledge, and ability in terms of going into jobs in water quality, city planning, aquaculture, biotechnology, NGOs, you name it. So there's a lot that is transferable. This is on the website, and what I'd like you to do is just sort of look at, is there a stick here, do you know? It's easier than pointing my hand, I guess not. I'll get a laser pointer next time. So take a look at this. This is KSAs, it's on the web, and it just tries to link what these are, what we're doing, and then continuity with other integrated marine science classes. So take a look and engage. Now, on this short version of the syllabus, I used to have graduate students who were on leave from the Navy, and I had one who was a commander in the Navy while he was getting his PhD with me, and he would come in and say something, and I'd glare at him, and he'd go, not a career move? So if you don't read that stuff, it's not a career move. So there's a reason, and I highly recommend you looking at it. Now, in terms of the course format, the way that I like to start every class, and tell me if you're going to be, if we can start at 5 past, that'd be great. But tell me if you can't get here, and then I'll make sure that you don't get messed up by us starting early. I'm going to have a quiz. The quiz should take less than 5 minutes. The homework from the week before will say what's on the quiz. The quiz is worth like all of 4% of your grade, but it gives me an idea of who's learning what and what you're getting. So there'll be a quiz at the beginning of every lecture. There'll be a lecture every week. There'll be a laboratory. If you can read it in advance, you'll be efficient and you'll be able to get out on time. Otherwise, sometimes things stack up, which is bad. Bring the lab document to the lab. The homework is going to be based on the lab. So when you write something down, don't walk out and put it in the blue tin, because you'll be using some of that information excuse me, for your homework. Take a look at the syllabus. The week of the 11th of April, you'll be expected to come. It'll be a short lab that week, but you're expected to come for 20 minutes sometime during that week. You'll form teams and you'll be doing a growth experiment. Sometimes they work fantastically. Let's hope this is one of those years that they do. The other one to write in your calendar is that in the lab on the 25th and the 26th of April, there'll be a laboratory practicum. What you do in Lab 3 is what the practicum is. And it's an incentive to make sure that you practice good chemical hygiene and good skills. And you'll sign up for appointments, and it'll be about 30 to 40 minutes. But make sure that you remember the week of the 11th, that there'll be something going on every day for one member of your team, and that on the 26th and the 27th of April, we'll have the practicum, and there is a final. It says it's down in 354 Aubert, but I don't think that's going to work, and I need to check with the staff to see where this is actually going to be. The homework, one of the things about, in my world, neatness counts. And so the way that I do my science is I have to get money for it. And I go to the National Science Foundation, I go to NASA, I go to the Office of Naval Research, I go to NOAA Sea Grant. And if I have a document that looks horrible, people immediately say, slob, can't do anything right. So professionalism in how you do a written document, how you present yourself in any way, really can give you the edge in terms of getting a job, getting an internship, etc. So take this as an opportunity. Seize the opportunity to practice and be professional in how you present your homework so that I don't have to, if I have to go hunting for things or I can't find something, to me, it's not there. It'll be on the website. It's best to ask questions. Before the weekend, just so that you make sure that you get an answer. This is where you've been sending homework to, right? So keep doing that. In my world, if I don't submit a grant proposal by the appointed time, it doesn't count. It gets thrown out. They don't even look at it. I just wasted a month writing it. So I do a late fee, and the late fee is in the syllabus. I also am really sticky because, like for the National Science Foundation, you have 15 pages. If you have 16 pages, they return it. They don't even review it. You've just wasted a month. So I want you to do a couple of things. One is a naming convention. I don't want my homework, .doc. I want your last name, the homework, the number of the homework, and then this should actually be PDF because I want you to convert it to a PDF. So I wanted your last name and the homework number, and I want it in a PDF. And the reason I want it in a PDF, and if you don't have a PDF, there are other programs that make something very, very similar, is that Word documents have a nasty habit of having things move around. If you lock it as a PDF, it's not going to move around. I'm going to see what you want me to see. I'm not going to see what Uncle Bill in Microsoft in Seattle wants you to see. Neatness and formatting counts. You can collaborate on the concepts, but the write-up must be your own because I want you to work. I want you to learn. And then the grading policy is on the full syllabus. So any questions about the course? It's just a little bit different. Yes?
Well, in the beginning of this class, we could see our grade on our homework and then turn it into a better grade. Do you have that policy?
I don't do that. But if you're having trouble, make sure you contact me. I do want you to do that. Any other questions? Okay, so units and dimensions in terms of a need for a common language. So the metric system, which unfortunately the United States and 2 other countries in the world don't use the metric system, but it's beautiful because it's base 10, and you just divide by 10. It's beautiful. It was proposed for the US in 1790, and the French, who developed the metric system, sent some prototype standards on a ship to the Congress, and the ship got blown off course, and it never arrived in time. Blame it on the ocean. And as a consequence, the vote to convert to the metric system in 1791 lost by 1 vote. Now it's due to a storm. Because if they had seen the artifacts in terms of here's a standard for length, here's a standard for weight, it's very likely that that one person would have been convinced and would have voted otherwise. And then there's a messy, sordid history in terms of metrics. That's too expensive. Yeah, children can't do it. But if you're interested, there's some beautiful stuff on, and I'll give you the NIST website. But SI units were introduced around the French Revolution. And here's Le Système International de Units, which is the derivation of SI, so it stands for System International. It's not SIU, I don't know why not, but it's SI. And, but it was developed by the French right around the Revolution. The 3 SI units that we're going to use are based on the meter and volume. There is no SI unit for volume. It's derived from the meter. Kilogram for mass, and it's not the gram, it's the kilogram. And then time is the second. And the reason this is so important is that in terms of reproducibility of results, you've got to have something that everybody buys into, and it has to be global. And one of the things that you can't avoid when you listen to the news or surf the web is that we're going global. And so you may wind up working in Greece, in China, in South Africa. I'd say the probability that at least 10% of you will be working someplace else is very, very high, and it may be more like 50% of you at some point. And so this is how the world works. And so this is how science works, but it's also how the rest of the world works. So that's super, super important. And we rely on units in our daily life, measuring in terms of cooking. Here's the famous Maine sign where you can go to Norway, Paris, Denmark, Naples, Sweden, Poland, Mexico, Peru, or China, and here you know exactly how many miles it's going to be. And notice it's miles. If you're going to build a house, here's the Pike Place Market in Seattle where they do the flying fish, and they chant as they throw a salmon to the person behind the counter, and then they weigh it, and they weigh it on a calibrated balance. So units matter. 1999, probably some of you know about the famous NASA Mars Climate Orbiter that in 1999 dollars cost $125 million, and it crashed. And the reason it crashed is that there were 2 groups, and one was using the English system and the other was using the metric system. And when they relied on this to get the maneuvers into the proper orbit, and it got messed up because the 2 different systems were giving incorrect information when they were trying to mesh them. And what happened was it entered at too low an altitude and it burned up. And so in 1999 dollars, that was 125 million. With inflation, we're probably talking $200 million, and people are still interested in Mars. So there was a really good chance, but units matter, and it got messed up. And I really love this little cartoon because it was published after that crash, and turned 4 longs to the east, then 2 rods to the right, 7 fathoms straight ahead, a peck to the south, no, make that a pennyweight, 13 cubic sideways, a hogshead down toward the final approach to the Martian surface. And these are actually all units of length at some time or another or place in history. And the little cartoon guy said, "What's a hogshead?" The guy who wrote these instructions. Joke. But the point is that unless you're speaking the same language, it makes it really hard. This is probably my favorite book. Probably only a geek would like it. And it's a really neat story, and I think it sort of sets the stage in terms of why you want this. So bear with me. I just want to read a page about the noonday cannon, and tell me when you see where this is going. For centuries, a remote seaside village on a distant foreign shore kept time by a cannon that a local military base fired at exactly noon from its perch atop a hillside. This was long before the days of the internet, even before television and radio. And in the village, the sound of the noonday cannon was a phenomena as natural as the rising and setting of the sun. a regularity that celebrated the day and divided morning from afternoon. The noonday canon shaped the stability and pace of the villagers' lives and was used to plan everything from business meetings to conducting clandestine affairs. According to this old legend, a teenage boy wondered how the cannon knew how to go off exactly at noon. So one day he climbed the hill and asked the artilleryman how he fired the cannon. The artilleryman smiled at the boy. He shot the cannon by the order of the commanding officer, whose duties included procuring the most accurate watch obtainable and keeping it carefully synchronized. The youth then approached the commanding officer, who proudly showed him the finely made and precise timepiece. How was it set? Well, on his weekly walk into town, the commander said, he always took the same route, which carried him past the shop of the town watchmaker. He would stop and synchronize his watch with the large and venerable clock in the watchmaker's window, one that many others in town also used to set the time. The next day, the youth visited the watchmaker. Can you see where this is going? And asked how he set the large clock in the window. By the only reliable way anyone around here has ever had, the watchmaker replied. I set it by the noonday cannon. The story of the cannon captures the habitual way we rely on measures. And in terms of measures, people locally would create measures. And it's only today that we have, through the SI units, the uniformity, absoluteness, and transferability to anyone, the ability to measure. And so I just want you to keep in mind that measures have been and can be relative, but it was really the process at the turn of the French Revolution that set in motion the idea of having a universal standard for making a measurement. And that's how we as scientists can make this tremendous progress. I just want you to think about what life would be without a measure. How many of you would want to get on an airplane if one air traffic controller used a different time? Maybe his goofy Newfie time. So Newfoundland, you know, is half an hour different than the rest of maritime Canada. But we absolutely depend on having measures. And so units give a magnitude to a dimension, and they've been relative to some kind of standard, and in many cases, those standards had been arbitrary. The oldest known standard for length was the cubit, which was from the elbow to the middle finger of the reigning pharaoh. So you could imagine if the pharaoh was a young man, a teenager when he became the pharaoh, this is going to be a changing unit. And if you didn't keep up to date with the growth of the young pharaoh, you could be put to death, which would not be cool. And every time the pharaoh died and you get a new pharaoh, then you had a new standard. And so that could not have been an easy way to do things. So it was until the 18th century, there wasn't any unified system. It was chaos. Supposing I said that I would pay you 100 and I would pay you 1,000. Well, 100 what per what unit of time? 1,000 what per what unit of time? Wouldn't make any sense. It would be chaos. And if you went from one town to the next, you know, how do you know what is happening and how do they do things? So it was really the beginning of global commerce, and it was the development of technologies that demanded that there had to be a better way to do this. And scientists jumped into this with, embraced it because science was becoming more and more collaborative, and there was a need for these universal measures. So universal and absolute. And today we have universal measures, but there is still one that is not based on an absolute physical principle, and that is mass. And I'm going to talk about that next week. But they're making progress. And so who are they? So there's a bunch of people, metrologists, who devote their lives to making this stuff work. And we assume that everything works really, really well, but it's based on these international conventions. And there's a Bureau of International of Weights and Measures that get together on some kind of frequency to look at every SI unit. So fantastic website is the National Institute of Standards and Technology. And they actually have suggestions on writing papers. And so I invite you just to go peruse this website, because there's a lot of interesting information and also historical information. So I've got the meter, the kilogram, and the second. And from that, and we'll talk about this more in a couple of weeks, volume is derived from the meter. So go back and look at this slide and make sure that you can do this conversion. That 1 liter is 10 to the minus 3 cubic meters, and 1 cubic meter is 10 to the 3 liters. And I'm going to ask you to do this. I want you, when you come out of here, do it in your head. Do it in your sleep. Do it while you're driving your car. Because in marine science, these are interconvertible if you're going to try to get a concentration of something. So commit that to memory. So here's the unit of length. And the initial unit was a pendulum, length of a pendulum, having a half period of a second. So now that's affected by gravity. So that didn't work so well. So then they wanted to do 1/10 of the length of the Earth's meridian, but it turns out that the search for the meridian was a lot more difficult than they had anticipated. So then in 1898, they used an alloy of iridium and platinum. And so here's a physical artifact, and they put little scratch marks on it. And I think the United States got number 27. And so they sent these all over the world. And the US one was off by 1.6 microns. You know, these are people who are trying to get down to no variation. So just think about how you would put scratch marks on a piece of platinum and then send it out, because that becomes the standard globally. In 1960, they used the wavelength of krypton. And then in 1983, they used the path traveled by light in a vacuum during a time interval based on the cesium clock. So there's some independency. So time is based on a cesium atomic clock. And this was done by the Committee of Weights and Measures. And I just wanted to say that this is going on all the time. You know, so there are meetings right now. This is metrology at the nanoscale. And for the women in the class, let's get some more women in one of the next ones. So maybe consider getting into metrology. They're probably like 10%. But, you know, this is only 6 years ago that there was a meeting talking about metrology at the nanoscale. So what are the challenges as everything is going into smaller and smaller scales? And, you know, as you know, some of the new computers are being built at nanoscales. So there's some commercial requirement for that. So orders of magnitude. As part of your homework, I'd like you to become conversant with some of these units. Now, some of them are not really used that much in the US, but you'll see pico, nano, micro, milli, kilo. And the other thing I'd like you to do is really get conversant with using exponents. So if I get a homework and you give your answer, and oh, by the way, do you notice what I just did? I put a period and I put a 0. Did anybody ever watch Abbott and Costello, the movie Niagara Falls? Do you know who Abbott and Costello was? You probably heard of Abbott. It's the old-time comedians. And I think it was Costello. He's locked up in a prison with this guy who's killed his wife. And if anybody says the word Niagara Falls, the guy turns and goes slowly. He turns and step by step, and then he starts strangling Costello. And he calms him down. And Costello says, well, I'm never going to say Niagara Falls again. And the guy goes slowly. He turns. Okay. I go ballistic if you don't have a 0 there. I go into a grocery store and they say 0.5 off today. And I go, where's your 0 in front of the decimal point? I'm driving on 95 through Providence, and they talk about toleration of less than 0.04 blood alcohol level, and I go, "Where's the 0?" And the people in the back seat go, "She's crazy." Okay, humor me. If I'm going to do this, and you don't catch that, whose fault is it? If you're going to suffer the consequences. So put that 0 there. Humor me, because I'll start taking off points. It's a good idea to humor me. So anyway, my point was, get used to exponents, because if you give me an answer like this, I am not going to spend my time going 1, 2, 3, 4, 5, 6, 7, 8 zeros. What I want you to do is use the exponents. Nobody is going to print that in a publication. Nobody, particularly people like me who have a hard time seeing, are going to count that. So exponents are your friends. Go to the web. There are great resources on the web. There's some great resources in the homework. So I want you to know what the prefixes are. I want you to use exponents. Anyway, yeah, marine science student too, right? So next week I'm going to ask you to be able to order them. And so here it shows, kilogram, it's just kg. Notice gram is just g, milligram is mg, microgram. And make sure you know on your computer, if it's a Mac, you push option M to get microgram. I don't know if it's the same on a PC. Nanogram is just NG, picogram is PG. So make sure that you're familiar. Sometimes in the literature, you'll see things only in grams, but very often you will still see these abbreviations. So just get conversant with it. We'll be using kilogram meter, from which volume is derived, and we'll be using moles in this class. Scientific notation, there's a homework problem on scientific notation, and there are some good references. And so, here's the point in terms of if you convert everything, it's a whole lot easier in your mind to do orders of magnitude with the exponents in terms of, that was the basis of the slide rule. I know everybody uses Excel, but you want to make sure you can tell when Excel isn't working. So pay attention to significant figures. And if you have an example in Excel where you divide some number and you get 0.12753892572 and the balance weighs to 3 decimal points, why are you giving me garbage? So make sure you understand what a significant number is. And so if Excel lets you do something like this, but the balance is only good to the 3rd decimal point, this is garbage in terms of an answer. Using scientific notation and exponents are going to help you with conversions to volume. And here again, this is on slide 26. Take a look at this and make sure that you're really comfortable in terms of going for the conversions with a mil, a liter, and a meter cubed, and just sort of play with it and work through it. Now the third thing about the class, The first one is metrology and water quality, nutrients. The second one is an emphasis on units. And the third one is an emphasis on traceability. And that goes back to NIST standard traceability. And the way that you know something is correct is you relate your measurement back to something that is NIST traceable, which is the National Institute of Standards and Technology. And what we'll do in the lab today is you're going to check a pipette. And the question that you're going to ask is, how do you know that the pipette is delivering what it's supposed to? And so the way that you can do that, and I'd like you to read the lab handout before you get to lab, is that 1 cubic centimeter of water, which is the same as 1 ml, at 20 degrees C, that equals 0.99826. I probably have this wrong, but what does it say? Look in your handout for the lab. It should be toward the back. I should have this in my memory, right? So bad me. (998) this is on page 4. 9982. Okay, I don't know that. It may be a 6, but no, it can't be a 6. So it's 9982. What else did I forget here? Units. Grams. So the mass, and we're going to be using mass and weight interchangeably, but it's mass. So 1 cubic centimeter of water at 20 degrees, not at 10 degrees. If you're going to the Antarctic and you're working at 0 degrees, you better do some calibration of your pipette, because water, pure water, gets more dense until it gets to 4 degrees, and then its density increases. And so that's why a lake will get colder, but it has to be unithermal until it gets to 4 degrees. And so that's why a lake will take forever, and then all of a sudden ice forms. So it has to be at 20 degrees and the mass. And so if you know that, you can calibrate your pipette by pipetting water, and we're pretty darn close to 20 degrees in that lab. And so the question you should next ask is, you're going to weigh this on a balance. How do you know the balance works? So the way you know the balance works is you get a calibration mass standard and you check the balance. And I'm going to tell you something. There'll be two kind of pipettes that you're going to be using. And one of them is a 1 ml pipette, and they're really, really good. The other one is a 5 mil pipette, and I think they should put the engineer in jail. Because if you let it, the barrel snap back really fast, you aspirate water up into the barrel of the pipette, and then the TA has to go around, and you'll be doing this a lot. Not with this class, because you're going to be perfect. Has to take it apart and dry it out. And so that means the 5 ml pipette is getting taken apart a lot. So when you're doing something and the volume really matters, it's a really good idea. The other thing I like to tell people in this class is, you're going to think I'm a terrible person, but and so what I mean by that, so I'm being a little bit facetious, but if you're doing your capstone and you really want to make sure that you're not wasting your time, you don't want to say that, oh, there's a solution in the fridge, I'll use it. and it was made up in 2008. Or, oh, you know, this pipette is going to deliver exactly what it says. You want to do some thinking for yourself, and you want to make sure before you go spend a lot of time that you know that your tools are really working the way that they're supposed to. So I'm being a little bit facetious, but I'm kind of not. You know, you get something from a manufacturer, you want to make sure that it actually works before you start using it. So here's the, since we're dealing with nutrients and salt, these are pictures from the air of the San Francisco salt ponds. And there's a phytoplankton called Denaliella. And the more salt, so it's green, it's a green alga. And the more salt that you have as these salt ponds, and they actually harvest salt from them. It's Cargill who sells them, sells the salt. And they're a big supplier of feed to animals and salt to the world. And so as the salinity of these salt ponds, as they're evaporating, becomes saltier and saltier, the Denaliella produces more carotenoids. And so they get oranger and oranger. And so if you're ever flying into San Francisco and they happen to bank in the right way, and you're lucky enough to sit at the window, look down and see if you can see some salt ponds, because depending on where they are in the evaporation process, you can see some absolutely spectacular ponds with, you know, really cool coloration. Any questions? Okay, I made it through lecture. That's great. You made it through lecture. So I'll see the 2 o'clock group, and then the rest of you I'll see next week. And just email if you have a question.